Hey APL class, we are going to get started with the section which involves implicit differentiation, and toward this end of this actually we'll do the second video for the logarithmic differentiation, which kind of goes hand in hand with this section. Okay, so the first thing we want to discuss is what does it mean for a function to be written explicitly. And what we're referring to when we say an explicit function, typically when you first learned equations, on the coordinate plane you just had x and y, you didn't use f of x that much. But what we're saying here is that y is a function that's all in terms of x. So this is just a parabola. We can see y equals x squared plus 1. So we're saying it's the function y that's in terms of x. It's explicitly written in terms of our independent variable. And so here, another way we could have written this one is with the f of x notation. So this is a function in terms of x. It's a function of x. So we have x as our independent variable throughout. So that's an explicit function. So our function f of x is all in terms of our independent variable x. We can have functions, and particularly when you get into some of the conic sections, we see sometimes we have the x's and the y's kind of mixed together, and they're written in a way that it's difficult to write an explicit form of the function. Sometimes you may have x's and y's on one side and you can isolate and solve for y. Some of these are real difficult, if not impossible, to isolate the y. And so sometimes we might run into one of those functions and we still want to find the derivative. So we need a different method of doing that, which is called implicit differentiation. So these functions be written implicitly. They're not explicitly solved for y, so that they could be written in the form f of x and then just all in terms of x. So what we're going to do is we're going to take a look at how we can do derivatives implicitly of implicit functions. Okay, and that is it's a follow-up of the chain rule is really what we're using when we do this implicit differentiation. So here with the first example, this one obviously it's not, there's no implicit differentiation necessary here, because it's just, our function is just x cubed, so it's all in terms of x. But just to kind of demonstrate what we're referring to, when we do the derivative of x cubed, right, we know that the power rule, we just bring that down, we say it's 3x squared. But what we typically don't say that would help demonstrate what we're doing here is because, the inside, or the, when we talked about the chain rule, I'd always say there's an inner function and an outer function. The outer function here would be the third power. The inner function is just the x, right? If it was anything other than just x, then we'd have to multiply by the derivative of whatever that was. So really what we would be doing here is taking the derivative of x with respect to x afterwards. And technically that's correct, but we don't write that because derivative of x with respect to dx over dx just cancels and becomes 1. So we just leave our answer as 3x squared. We typically don't show that step. However, the reason that, because what we're doing is the derivative of whatever they give us here with respect to x, right? That's what that dx means on the bottom. So over here, if we're taking the derivative of some function, and this one's in terms of y, but with respect to x, we can still use our same rules, which would be 3y squared, but then we have to multiply by the derivative of the inner function y with respect to x. So that means I have to follow this with a derivative of y, dy dx. And that's the way I leave that expression, and this is what we're going to see a lot of when we start doing the implicit functions that have y's mixed in there that we can't just isolate over to the other side of the equation. So anytime that you're taking a derivative of a term that contains this y variable, which is typically, we'll be working x's and y's mostly, then, if we're doing it with respect to x, then we have to follow with a dy dx, okay, because really it's that chain rule idea. Taking the derivative of the outer piece, which is our power rule, and then multiplying it by the derivative of the inner part of the function, which is just y. So the derivative of y with respect to x. dy dx follows. Okay. All right, and the next one, so we have, two different terms here. One of them is x, one of them is y. So with the first one, we take the derivative of the x, so it would be 1, and then that would be dx, but I'm not going to write that because we don't have to. But then plus, and then I'd have 1y, but then it would be, it would just be 1 again, but it would be then times the derivative of y, which would be dy dx, right? You could put a 1 in front of that if you wanted to. So derivative of x is just 1 dx, plus the derivative of y, which is also just 1, but then you'd have to put dy dx after that. So this would be our derivative of that expression. Okay. All right, next one. Now we've got a product rule, x times y squared. Okay. So remember, when we do our product rule, we go derivative of the first times the second. So the derivative of the x is just 1 times the second, leave it alone, so that's just y squared, 1 times y squared. So 1 times y squared plus, and then it's the first times the derivative of the second. So the first, x, times the derivative of the second, which is 2y. And remember, we have to do the dy dx. Anytime our term contains the y, we have to do our chain rule there, dy dx. So that would be what our derivative of this expression look like. We might clean this up and just say y squared, and then plus, probably say 2xy dy dx. Just to make it look a little neater. Okay, so that's the idea. So anytime that you're taking the derivative of a term that contains y, we're going to use the chain rule and take the derivative of that y with respect to x. Okay? All right, so guidelines for implicit differentiation. We're going to, no, what we're talking about here are going to be functions. So these were just expressions. They're saying find the derivative of this expression in this one. Now what we're going to have is like an equation with x's and y's possibly on both sides. So differentiate both sides with respect to x, like what we were showing here, derivatives with respect to x. Okay, collect all the terms containing dy dx. So anytime you had a term that had a y in it, and then you're going to get, you know, a dy dx, you want to collect all those terms on one side of the equation. Okay, so on the left side usually. And then all the other terms go to the right side. You're going to factor out that dy dx, and then you'll divide to solve. So here's pretty much what the process looks like. This would be a pretty basic implicit differentiation problem. All right, so as we go through this, so derivative here is going to contain a dy dx. This one is, the x squared won't contain one. But, so as we go through, we're going to have 3y squared dy dx plus 2y dy dx minus 5 dy dx minus 2x. Don't need a dy dx there. It could be a dx, and we don't have to write that. And then on the other side, since it's just a constant there, derivative of a constant is 0, so we end up with 0 there. Okay, so now we've got all three of these terms that have dy dx is on the left side. Let's just take this other one and add it to the right side, and we'll factor out the dy dx. I'm going to do this all in one step. So I'm going to factor out dy dx out of these first three terms. And then I'm going to add the 2x to the other side. And now we're trying to solve for the derivative of y with respect to x. I've got it factored out now. So all I have to do is divide by the 3y squared. And that would be my derivative right there. So dy dx would be 2x over 3y squared plus 2y minus 5. And that's how we'd leave our answer, just like that. Okay, so hopefully that's making sense. All right, next example, it says consider the equation here. So we've got, it looks like an ellipse, so we've got an equation for an ellipse. If you studied conic sections, usually this would be, you'd divide everything by, you'd make a 1 there, so you're probably more used to seeing it like this, where you'd have, so that would just be x squared over 4 plus y squared over 1 equals 1, something like that. And then, you know, so my major axis going left and right, the square root of 4, which would be right 2 and left 2, and minor axis up and down the square root of 1, which is 1, so then we get that elliptical shape there. Okay, so find dy dx for the equation above, and we're going to be better off just leaving it, I think, in this form to do the derivative. So when I do the dy dx here, so derivative of the x squared is 2x, and then the next one I would have, oops, so I'm going to have 2x, and then I'll have 8 plus 8y dy dx equals 0. And then I just want to solve for dy dx. So subtract the 2x to the other side, divide by the 8y. Divide by 8y. So I'm going to end up with, go over here dy dx equals, and I can reduce that negative 2 over a to negative 1 over 4. So I'll have negative 1x over 4y, like that. Okay, so that would be our derivative there. And so the next thing it asks us to do is to find the slope of the tangent line to the curve at the point square root of 2 and negative 1 over square root of 2. So the slope of the tangent line basically just means we're just, well, we're going to actually find the equation of the tangent line, so we need the slope, and then they give us the point, right? So, so the first thing is just to plug this in. So the notation we would use, we could say dy dx evaluated at the point square root of 2, negative 1 over square root of 2 might be a notation that you would see for that. And so showing that's what we're doing, we would just plug these values in. So I'm going to have a negative and a square root of 2 on top. Then I'm going to have 4 times negative 1 over square root of 2, which would be like negative, so I'm going to have 4 times negative 1 over root 2 on the bottom, like that. So we get kind of a complex fraction here. And so let's just say at negative root 2 divided by, I'm going to put that over 1. So let's multiply by the reciprocal. So down here I would have negative 4 over root 2. And so I'm going to multiply by root 2 over negative 4. Hopefully that makes sense to you that I'm doing it like that. And then that would just become on top, I would get positive 2, and on the bottom I'd get, the negatives are going to cancel, negative times negative. So 2/4, which should be 1/2. So my slope should be 1/2 right there. Okay. And then on part D, find the equation of the tangent line. Well, that's just going to be y, what did I do there? Get my highlighter button. So we're going to go y minus the y coordinate, actually plus then 1 over root 2 equals slope of 1/2 times x minus square root of 2. So that would be our equation of our tangent line right there. And then it says write the equation above explicitly. So this happens to be one where we can solve it for y. It's not too difficult to do that. So if I were to solve this equation for y, I'm supposed to write it explicitly. And then we can graph it just to verify it's the same. I don't know if you really need to do that. It's going to be an ellipse still. But then it says once you do that, okay, take the derivative explicitly and compare it with the result that we got in part B. Okay. Well, the original equation was x squared plus 4y squared equals 4. And so if I'm going to solve this for y, I would first subtract the x squared. So I'll have 4y squared equals 4 minus x squared. And if I divide by 4, y squared equals, so dividing everything by 4 there, I would have 1 minus, and then I'd have like x squared over 4. So I divide both those terms by 4. And then finally I'd do the square root, so I'd have y equals plus or minus the square root of 1 minus x squared over 4. Okay, so there's my explicit form of this. Okay, so if I'm going to do the derivative of this now, what I'm going to do then over here, so my dy dx would then equal, so if I use, this is technically to the, right to the 1/2 power right here. So if I would bring down a 1/2, oops, then I would have 1 minus x squared over 4 to the negative 1/2. And then I'd have to multiply, and I'd have a chain rule, so I'd multiply by the derivative of the inside piece. And so that this 1 would disappear, this part here would just become, so this would be like, you know, negative 1/4 x squared. So if I use the power rule, hopefully you can follow, that would just become negative 1/2 x to the first for that part. Okay, so this was using my power rule here, so this was to the 1/2 power. Let me rewrite this. This would be power. I'm just going to leave the plus or minus off for right now. So I'm going to bring this this 1/2 down and take away 1, so I end up with this. Then the derivative of this inside piece, x squared over 4 is like 1/4 x squared, so if I do the power on that, to do the derivative of that, I get negative 1/2 x. Okay, and then if I clean this up just a bit, dy dx, that would equal, if I multiply these together, I'd have like, let's see here, I would, on top, what would I have? I'd have, well, when I do this part, you know, I multiply a power to a power. Oh no, this I'm going to drop down to the denominator. So I'm just going to keep the 1/2 x on top. So I'm just going to have like a negative x on top. And then on the bottom, I'm going to have the 2 times the 2, which is going to be a 4. And then this whole expression here would drop down and become, you know, to the positive 1/2, which would just put it back under a square root. 1 minus x squared over 4, like that. Okay, so there's my derivative that way. And now I'm supposed to compare this to the answer that I had before. Now the answer I had before was this, negative x over 4y, which looks a bit different, but let's take a closer look. Y, right? We don't have any y's in this one, so what does y equal when I simplify? So it's negative x over 4y, right? Well, I have negative x over 4 and then this expression, but really isn't this expression equal to what I have for y right here? Now, I do have the plus minus, and I kind of left that off, but you know, that plus minus could get brought back out here. But just for simplicity, to show that this is the same thing, I just left it off. But yeah, so we can see y right here, that's the expression that I had. So negative x over 4y, this is the same thing if we do it explicitly. Okay. All right, and then the last couple examples, I've got them worked out to save a little bit of time here. So we've got kind of a weird function. It looks like almost like a figure 8 diagonally in the coordinate plane. But so here's what we've got here: 3 times quantity x squared plus y squared, and that quantity squared, and then equals 100xy. Okay, so we're going to find that. It says find the slope of that equation at 0.31. Okay, so the sketch of it I just did a screenshot of Desmos and put that there, but that's what the graph looks like. Okay, now if we do this derivative, okay, so I'm going to use power rule 6, and then this part stays the same, x squared plus y squared, and then to the first power, drop that down. And then the derivative of the inner part is going to be 2x plus 2y dy dx, because that y, I have to put a dy dx there, equals, and then on this part here, we've got a product rule, so that's going to be, you know, 100, which we could kind of distribute through at the end, but derivative of the first times the second, so that'd be just 1 times y, so I have 100y there, and then I'd have the first times the derivative of the second, which is x times the derivative of y, which is right here. So I get that expression. Now up here, I'm going to have to, in order to, you know, I have to get all the dy dx terms together, and if I'm doing a product here, I'm going to have to FOIL this out and just combine any like terms. So when I FOIL this piece out, distribute the x squared through there and the y squared, collect all my like terms, I'm going to end up with this expression right here. And distributing the 6 through is going to give me this expression with some 12s in it. And so I've got a couple like terms. I've got a 12x squared y dy dx and a 12, let's see here. Well, these are the not like terms, but these are the terms that contain the dy dx. So I'm just going to keep those on the left side of the equation. All right, and then this term over here with dy dx, I also want to move that over to the left side of the equation as well. So this term stays here, this one is here, and then the plus 100x dy dx, I subtracted that to bring that over. Okay, and then these two terms that did not contain dy dx, I moved those over to the right side of the equation. All right, so that means I would factor out the dy dx from all 3 of those terms, right? And then I would divide by these 3 terms. So the 12x squared y plus 12y cubed minus 100x, those all end up in the denominator underneath this expression here. Okay, and then I was supposed to evaluate this at the 0.31. All right, so what I could have written here for a notation, I guess, instead of just that, could have been, back to my purple here, I could have said dy dx, and then they go like this, and then evaluate it at 3, 1. And so that's what I do at this point here when I'm substituting. Okay, so just plugging in a 3 for the x's and a 1 for the y's, you can do the calculations there, but what you end up with is negative 260 over negative 180, simplifies down to 13/9. Okay, so just a lot of algebra involved in this piece, but hopefully you can see how the calculus plays out there. And then the process of implicit differentiation is to collect all the dy dx's on the left side, move all the other terms over to the right side, factor out the dy dx. I didn't really show the factoring piece, but if we factored it out, we'd be dividing by these 3 terms at the end. Okay, so we get this, and then divided by these 3 terms here. Substitute in 3 for x, 1 for y, and we get this fraction right here. Okay. One other thing for this video is finding a second derivative implicitly. So for this one, we have an equation. This would be an equation of a circle, and we do that derivative. We get 2x plus 2y dy dx equals 0, because we're doing derivative of 25 is 0. Okay, and then we're going to divide out the 2y, and we end up with negative x over y, right? All right, so this is where I'm at right now. And now if I'm going to do the second derivative, okay, so the notation for that is d, looks like squared, d squared y over dx squared, okay? And so it's the second derivative of y with respect to x twice, okay? So that comes out here. And so that's my second derivative notation. So this is a quotient. So low d high, so low is y, d high would be negative 1, minus high d low, so d low would be dy dx, all over the square what's below, so that's all over y squared. So that's my expression there. And so if I clean that up just a little bit, I'm going to have negative y plus x dy dx all over y squared. And then what you want to do, you don't want to leave this dy dx here. You want to substitute in. That's your first derivative. So you can take this expression, plug it in right there, like what I'm showing here, and simplify again. So if I were to take this negative x over y squared, put that in there, or sorry, just negative x over y, and then I, times this x, I would have negative x squared over y for that term. The other terms stay the same. And just to clean it up a little bit, because I have a complex fraction, to cancel this denominator, if I multiply a y to every term there, and then I have to do the same on the bottom, that would give me negative y squared minus x squared over y cubed. Okay, so that's an example of a second derivative. So that's it for this first part of these notes. We'll do the logarithmic differentiation in the next video.